Hi everyone. My name is Piotr Betkier, and I will talk about a topic that I find very important, but maybe it's not discussed too much. It's about building internal tool ecosystems, so internal frameworks, libraries, so-called company commons. So Spring is often used as the base for such tools because it's so extensible, battle-tested, it's so popular. So I want to share my views because I've seen a couple approaches in a couple of companies, and especially right now at Allegro, I'm in a team that, among other things, is developing such internal commons ecosystem for our microservices-based architecture. And I have a few thoughts from that. So we will go through how our commons evolve and what we found to work for us. So hopefully, after this talk, you'll have many ideas how to enhance your own internal tools and, in general, how to write useful open source tools. So quickly about us, Allegro, we are an e-commerce site, mainly in Poland. So in Poland, we have around 50% of e-commerce market share, so it's quite large. We have quite a lot of users and traffic. But I think the IT perspective is more interesting. So from the IT perspective, our story is a classic story you hear lately. So we used to have a huge monolith written in PHP from the 90s. It was, I think, like 2 million lines of code, just total mess. We couldn't develop in it anymore because it was so complicated. So we decided to build a better new world with JVM-based microservices. So 4 years ago, this microservice revolution started. Right now we have around 400 services, over 1,000 instances in production. Right now we are kind of split between this monolith and the new world of microservices. So building microservices means that you have a lot of projects running on a shared infrastructure, right? There's a lot of common code that would be duplicated in these services. So you need tooling that will cover all these common things for everybody so that people can deliver features quickly and not reinventing the wheel every time they start a new project. So 4 years ago, that were times when Spring Boot was still a toy. It was not that mature, I would say. There was no Spring Cloud. So basically, we had to do something on our own. So the first approach we took was to create our own all-in-one framework. So we grew our internal Spring-based framework. So it was called Commons, because how else would you call a framework like that, right? It's a common name in many companies. So it was a single project, multi-module project that contained a couple of modules, and it declared a lot of dependencies. So it had everything you would need to start a microservice. So it had Spring, of course. It had Jersey as a REST client. It used drop wizard metrics, Zookeeper for dynamic configuration, Swagger, log/stash appenders, helpers for writing end-to-end tests, all the things you would need to write a microservice. So basically you would throw in these commons as your dependency, and then you would auto-wire some beans from this framework and write your business logic. So all the technical aspects were taken care of by this framework. This framework was highly opinionated, so it made decisions like which REST client to use. You had to use Jersey because all the things like, for example, discovery, service integration, and things like that were written against this REST client. Basically, you just threw in this dependency and could code. And how would you run such applications? So you would use some factory method to build an application, then call run, and then the application context would start. It would locate your application context XML to load your beans, and then the application was set. So this framework was a solution that worked for us just in the beginning. So it was certainly easy to write. because it was just a single project. It declared all the dependencies, and that was it. So it was easy to, let's say, model your commons this way, and it was easy for the teams to start because they just threw in one dependency, and then they would, code according to some blessed technologies. And it's a solution that I find in many companies, like creating this common framework that you use. But it may work when you have a small number of projects, but for us, we quickly hit the wall. So first of all, it was hard to customize. So for example, let's say some team wanted to use, I don't know, some different REST client, not Jersey, maybe some different REST client. Well, they couldn't because everything was expecting that you have this Jersey client. And for example, Discovery Service integration wouldn't work with your new tool. Or let's say you wanted to drop some feature. For example, you don't need Zookeeper dynamic configuration. Well, you still had Zookeeper on your class path because, it was one framework with all the dependencies. So it was hard to customize. It was also hard to evolve. So the people writing this framework had trouble releasing new versions because they were breaking compatibility because they didn't know, how the framework was used. There was no such concept as public APIs, private APIs. So people were using this framework in different ways. And then, from version to version, things weren't compatible. And probably the saddest thing was that it was not for everyone. So this framework expected you to use Spring. So what about people, for example, that do some Scala-related stuff because they do some data processing, for example? Well, they couldn't use this framework because it was based on Spring and related technologies. So basically, they had to code all the infrastructure code by themselves and try to be compatible with the conventions that we had in this framework. Basically, it was, as you can imagine, it was very hard. So it was a simple approach that worked in the beginning, but then we quickly noticed that we cannot develop like that anymore. So we took a different approach. So now we started with a different philosophy. We started creating a family of libraries. So the library, so for example, that's the libraries that we would have. We would have a library for reading cloud metadata. So an application can know what is its IP address and in which data center it is located and things like that. There was a library for tracing, for example. So we were hiding complexity of some Zipkin-related technologies under a simpler API. For example, metrics, we would code some conventions on top of Drop Wizard metrics, Discovery Service client for integrating with our Discovery Service mechanisms. So things like that, wrapped in focused libraries that would do one thing, do not depend one from another, and are agnostic when it comes to technology. So they are written in plain Java. You don't need any framework to use them. You just drop them, throw them as your dependency, and that's it. And you can use them or not if you want. So quickly, how would you use such library? So no Spring, no any other technology. You just call some builder, right? You configure it, and then you can use it and get some plain old Java object, right? So that lets you construct your application using these libraries as building blocks and doesn't assume that you use Spring or any other technology. But as you can imagine, if you have a lot of services, then probably most of them would use Spring or some other technology, and all these libraries would have to be configured in each service. And configured in some similar way. So starting a new project would be very tedious, right? Because you would have to configure all these libraries once again, and this configuration would be duplicated in every service. So we created a framework for that, but it's a framework with a different philosophy. So right now it's Spring Boot Starter. So we have a Spring Boot Starter that does the default configuration. So what this starter does, it's pulling all these libraries, it's configuring them in some default way, And that's it. There's no logic or almost no logic in this starter, in this framework. It's just glue code for pulling these libraries. So you can disable certain features using some properties, or you can override the default configuration because we use conditional on missing a bean from Spring Boot, so that you can override the defaults if you want. And the most important idea is that this starter is completely optional. So if you want, it's the easiest way to be compatible with our infrastructure, use this Spring Boot starter and have everything out of the box. But if you want, you can configure the libraries by yourself and use these libraries to be compatible with our infrastructure without Spring Boot. So this is an approach that works for us for 3 years, and it showed us traits of successful libraries, because we write so many libraries. So we saw what makes our libraries useful and what makes them not useful. So this is something that I want to talk about for the next couple of minutes, what to have in mind when you build a library in order for it to be extensible and to be useful over the years. So first of all, we want our libraries to do one thing and do it well. So that will let us compose, replace, and evolve these libraries. So people will be able to build their application using these libraries as building blocks. So we want these libraries to be cohesive, focused on one thing, loosely coupled with each other. So one thing to have in mind is a single sentence rule. So if you can describe what your library does in a single sentence, then probably it makes sense. But if you need a couple of sentences to describe what your library does, then probably it's doing too much. So as an example, let's say we are writing a discovery client, okay? And a discovery client is a library that is able to register your service in some central registry of services. It's able to unregister it, and it's able to query this storage to ask what are the IP addresses of a given service. So because we have communication with some storage, probably we want some statistics, for example, latency to such storage. Let's say it's Zookeeper or Console or any other tool. We want to have these statistics to monitor how our applications are communicating with it. So a good way for doing that is saying, okay, so my client exposes certain statistics, and I don't care what you do with them as a user. You can probably send them to some metric store or something, but it's your job. You do it. And the wrong approach would be to code these metrics abstraction in the discovery client and have the user, register some reporters that would use these metrics model of the discovery client, because metrics and monitoring is not in the scope of discovery client. So doing one thing and doing it well. Next, being technology agnostic, so making as little assumptions about the technology stack as possible. So one way of modeling a discovery client could be saying, okay, so everybody is using Spring in their organization. So let's say our discovery client would be configured in a way that we have a Spring configuration, and there we define some beans. Maybe the discovery client could be a bean. We define some post contracts so that we can register our application during startup. We define some bean post processors, for example, to register some REST template interceptors so that they understand this service name protocol and to resolve it into IPs and things like that. And then a user would import such configuration, or maybe use auto configuration to automatically have it applied. And then he is expected to have a certain property in his context so that everything works fine. So This is very dangerous because now you limit your potential adopters, because now in order to use Discovery Client, everybody needs to use Spring. So these Scala guys who wants to use Scala frameworks, they are not able to use this. So they probably either have to use Spring even though it doesn't fit their case, or they have to re-implement things by themselves. So you don't want to drive technology decisions as being library developer. You want developers to be free. So what we can do instead is to make an agnostic, technology agnostic tool. So here we have a Discovery Client modeled in a completely technology agnostic way. We have a builder, okay? You provide some configuration, and then you call build, and you have a ready Discovery Client. And now you can put it as a bean in your Spring application, or maybe do some crazy stuff if you're using Scala or something. But it's your responsibility as the user of such library to put this Discovery Client as a component in your framework. And then this Discovery Service Client exposes certain methods. So it exposes method for register that you are expected to call during startup. Unregister, you're expected to call it before shutdown. And then when you want to find an IP, an instance for a given name, you call it when processing your request. And I, as a developer of this library, don't care how it's done in your technology. And this way, it's available for everybody, and it's much easier to test because this scope is very, very small. But again, if 90% of your company uses Spring, then this integration with Spring would be duplicated in every single service, and that's not something that we want. So you want this common configuration to be written once. So what we can do is to provide additional modules. So we would have a discovery core that is written in plain Java. It doesn't depend on any technology. And then you have different modules that provide integrations with different technology stacks. So for example, Discovery Spring provides configuration for Spring, right? Like REST template, interceptors, and things like that. So another way you can do it is to have everything in a single module, but have certain packages that contain these integrations, but have the dependencies to Spring, for example, as provided, or in Gradle it's called compile only, so that you don't pull Spring dependency onto your user's class path, but you expect your user to have Spring on their class path if they want to use classes from this integration package. If they use Scala, for example, they would only use classes from core. So somehow related, we want our libraries to have minimal dependencies. So ideally, we want our libraries not to depend on any other libraries. Why? Well, because of version conflicts, because we impact our user's class path. In Java we have flat class path, so if we pull some dependency, then maybe it will conflict with a dependency that a user already have. But it's not only about versions. It's about, for example, cases like left path case. You are probably aware of the situation in the JavaScript world when one of the really small libraries went missing from the package manager, and then the whole JavaScript world basically stopped building because they, the major frameworks, couldn't resolve their dependencies. So of course, things rarely go so extreme that your dependency is missing from the package manager, but there are things like security bugs being coded into newer versions of your dependencies, or maybe your dependencies start pulling another dependencies, and it makes things worse. So an example of that would be, imagine we build a library and we have a method that does something with a name. Our names are formatted in a way that they contain some parts separated with dots. And we want to do something with these parts, whatever it may be. So what first thing we need to do is to split this name into a list of parts, okay? And we know that in Guava there is a nice API for that. We have splitter and it has split to list. So if we were building a service code, like a microservice, not a library, then it would be reasonable to just use Guava and forget about it. But since we are using since we are building a library, we shouldn't do it because now we are pulling Guava in version 20 into our users class path. And what if our users need to use Guava in version 15? Then it may be a problem. Or some years later, they need to use Guava 30, let's say, and we need Guava 20. It makes problems. So a simple approach, just do it yourself. Basically, making a split to list is a quite basic task, so you can write it by yourself using JDK, and that's it, and you don't need your Guava dependency. Another approach, just for the record, it's called shading, where you can replace your dependency on some library, or maybe put it in other way. You can rename the classes, rename the packages in your dependency into something else, and package these different classes, these renamed packages, as a separate dependency. So for example, Jersey does it. They use Guava, but they don't depend on like Google.com Guava. They depend on their own Guava distribution that basically has packages renamed so that they don't clash on the user's class path. But this approach comes with different problems. I don't want to talk much about it. We don't use it basically at Allegro, but it's something that is useful to know. And lastly, having minimal dependencies means that we need to code our libraries in the lowest common denominator language. So what I mean is, let's say, for example, Groovy. I like Groovy for writing my services. It's it's a neat language, or Kotlin, but I wouldn't write my library in Groovy or Kotlin, because then I would throw Kotlin or Groovy runtime into my user class path. So again, he would have all these this whole jar in their class path. Maybe it would clash with some other version they're using. So basically, our libraries should be written in plain Java, because that's the lowest common denominator language on the JVM. So for example, Swagger used to be written in Scala, and it was a shame, because if you wanted to use Swagger, you suddenly ended up with Scala dependency on your class path. And if some other tool needed Scala in some different version, then this thing couldn't work. So right now, Swagger is written in Java, and everything's fine. Yeah, clear entry points. So one thing we see as being very helpful is being clear where the whole API of your library is, so that we don't ask developers to search through the entire code base, searching for things they can customize. So a good way for doing it is to make a builder. So everything you can configure in this discovery client, you can configure in this builder via this builder API. And if you cannot customize something using this builder, it's not possible to customize this. So if you want to provide a different load balancing algorithm, you just implement some interface and you provide it like that. Another approach we could think of would be, well, let's say we have a default discovery client and we want to customize something. Let's extend from this discovery client. And for example, let's override this pick instance method so that it's doing something else. It may look like it's not a big difference in the beginning, but then when you evolve this library, you cannot be sure that when you change something in this discovery client class, that you actually don't break any client that is subclassing your default implementation, because you don't know because the user that is overriding this pick instance class, he doesn't know in which context you expect this peak instance to be called. You basically don't know which methods do people override, which they don't. So it's easy to break your clients when you update this superclass. So basically, composition is better than inheritance, also in library code. And also, we try not to do things like that. So, like forcing our users to extend from some base classes. So let's say we would do a library for mapping exceptions, and we could, for example, model it in a way that we expect our users to extend from some common exception, okay? Or maybe we write some ORM tool, right? And we expect our users to extend from some base entity class. And it's a bad idea because then your users have dependency on your library code all over their code base, okay? Every exception they have has a dependency on your library. Every domain object they have has dependency on your library. And then it's difficult to test such objects. It's difficult to get rid of such library. Basically, it's polluting the code base of our users. So whenever you can, just stick with composition. And if you really need to model something as inheritance, be explicit about it. So say that this class is abstract or base, and you are expected to extend it, but only these methods should be overridden, and that's the contract, when they are called and things like that. So we talk so much about these entry points because it's really crucial for making your library evolvable over time. Because if we have a small surface of contact, so the contact between the user's code and your library code is very small, then as you can see, this green area is pretty large, and that's the area that you are able to refactor, change in mechanics of the library across different releases. Because the red area, that's contact surface, is the API that you need to keep between releases, but all the green area you can change without problems. But if you model your library like that, you have a large surface of contact, then this green area is small, and you can reach a point where you no longer can develop your library because you're blocked by the API that are still need to be kept between releases. So the smaller the surface, the longer you can develop your library and respond to changing requirements. And that's very important because public APIs are forever, so you have one chance to get them right. Of course, if you are building an internal library, then breaking compatibility is an option. I mean, you can contact every developer that is using your library, help them migrate, maybe write an email to everybody like sorry, we need to change it, provide assistance and things like that. But when you're building an open source library and you're breaking compatibility, basically users will lose trust and find something else. So it's important to make the APIs right from the beginning, because if you don't, you have a lot of work. So you need to keep compatibility. So one approach, one example, let's say we create some worker objects and we have a factory method where we provide name and some parameter, okay? But then you realize that actually there are going to be a lot of parameters, so it would be better to use a builder. But you cannot just remove this factory method create because a lot of people are using it. So what you should do is you should keep them both. A nice thing you should do is you could replace the logic, as you can see, replace the logic under this create API to use your new API. That way you no longer have to maintain both mechanisms. You right now maintain only this mechanism, and you just delegate to this new API. And over time, over time you can mark this as deprecated and basically probably remove this create method in the future. But it takes time. It's even harder when we are talking about protocols. So what I mean by protocols, the things that we talked about before, that was an API that is used inside one application. But a protocol is a way that many applications communicate with each other. So a protocol would be something like our health checks are exposed on a status health endpoint. Or maybe that we have some header, for example, for correlation ID. So we have some certain header with a certain name in a certain format that services exchange with each other in order to communicate something. So we cannot simply change the format because that's everything would break. So an example, let's say we have a correlation ID header. So each cloud is a different service. So service on the left is calling two services, and it's sending along the HTTP request. It's sending the correlation ID header with some number. Okay. So let's say our format is that correlation IDs are numbers. That was a good idea. But then we realized that numbers are too limiting. Maybe our correlation IDs should be any string. So any string should be possible. So we decide to update this first service and start sending correlation IDs as strings. But our services no longer can read. They cannot understand this correlation ID header, and everything breaks. So what you need to do is to first update the readers so that they understand both numbers and strings. And then you can update the writer so that he will write in this new format. And then later, once everybody is migrated, you can remove the support for this old format. It looks quite easy when you have 3 applications, but once you have like 100 or more applications, it's basically impossible to update everybody without something breaking. So it's important to think through the protocols very well from the beginning, because changing them in the future is going to be very, very hard. I mean, you will have to have some downtimes or something, or the feature will not be working correctly for some time. So how to approach this? So basically, one thing, we need to keep our APIs private by default. So if something doesn't need to be public, then keep it private. That way we can ensure that our users are not using it like in a way that we didn't think of. And we can be sure that this small API that we provide is the only way that people are using our library, and we have more options. And when creating new library, and especially when creating API, and especially when creating new protocols, we need to work closely with our clients. So things like creating proof of concepts in the beginning, having some early adopters using these proof of concept features, saying how they like the API, is it useful, marking certain features as incubating, as beta, saying that the API can change in the future. So when you agree on some API, when you are finally ready, you are sure that this API will be solid. It will not have to be changed in a month. And that's related to sticking to the vision. So as an author of a library, it's important to have a vision for the library and make sure that the library keeps on its path. I once was looking for a library on GitHub that was doing something, and I saw a library that could be useful. And when I read the README, it's unfortunately the author of this library said that this library is no longer maintained, it's no longer developed because community destroyed my project. This community destroyed your project. And then he explained that this library was very useful, and then people were providing pull requests and ideas for changes, and he was happily just merging everything and happy that his library is so flexible and can be used by everybody. But then quickly this library became just a huge mess of everything anyone could think of like using in their lifetime. So basically it was totally bloated, it was unusable anymore. So the project had to be like frozen. So we don't want to be like this guy, this poor guy. We need to have a vision, and it's okay to say no. I mean, even though we have an internal library and it's called Commons, it doesn't mean that everybody can throw what he likes. You know, we have to have a bigger picture and to really think of where it will lead our project, like in a year. So users come with ready solutions. You know, when a user uses your library, he may come up with an idea like, I need a third parameter that will do something, and maybe he will provide a pull request to add this third parameter. And you know, instead of merging it right away, it's a good idea to take a step back and think about what this solution is trying to solve. What's the problem? What this person is trying to solve? Ask for requirements. So maybe you will find that what this person is doing, you know, it should be a general solution. It should maybe be a different library or a completely generalized solution, not just some third parameter. Or maybe what this person needs to do, he thinks he needs this third parameter for doing something, but actually what he's trying to accomplish is dangerous. He shouldn't be doing it at all, but he just doesn't know that yet. So you can guide him for the better way. So that's related to something we had during keynote. So it's not that our libraries should be flexible as possible and useful for everybody. That's something I thought building tools is like a couple of years ago. I thought that building tools was, you know, making sure your tool can solve any problem in the world and can be used by everybody. But now what I see is that libraries should be easy to change in the future. So sometimes it's better, you know, not to do something in order to be able to respond to changing requirements in the future, because that's the main usefulness of the library. So things like deferring making decisions to the last moment when you have an idea for some feature, for some new solution, like don't go all the way, you know, creating super generic solution that will solve all the problems. Just make a smallest step that is sufficient for now and leave your options open for the future. If somebody needs something more complicated, you can add another step, but you leave your options open, and you know, maybe in a couple of months you will have a better idea, better use cases, and will know how to model this feature better. So real use cases are the key. All right, and when it comes to like actual code, make sure it contains no magic. So of course it's something that is a tip that is useful also when you're writing your services. But when you're building libraries, this code is read by a lot of people. It's not only your team, your developers doing this library, but also all the users debugging through this library, people trying to contribute, etc., etc. So make sure, you know, it's as simple as possible. So no crazy things like reflections all over the place or some very weird constructs. If you need to use reflections or difficult stuff, then, you know, wrap it in some utility classes, so that your main logic is, you know, very readable, and all the difficult technical stuff is really wrapped in some single place. And also, you know, don't use some weird external tools like Lombok. I mean, if you want to use Lombok in your services, that's fine, but using Lombok in library code is a very bad idea in my opinion, because then you require all your users to have some custom plugin in their IDE in order to debug through your library or to develop. And of course, there may be some problems with compatibility when next versions of Java, for example, are released. So, like, when you're building library, then as a tool maker, actual writing code is not taking you so much time. Mostly you spend your time discussing with your clients, gathering requirements, modeling your API, and actually coding the classes is pretty quick. So it doesn't take that much time. So optimizing it through using some tools that generate getters and setters for you, it's well, basically it's optimizing the wrong thing. So keep it simple, keep it readable, and be as explicit as you can. Yeah, and last point about libraries is being developer friendly. So keeping your developer in mind. So by things like providing reasonable defaults. So maybe if you are writing an HTTP client, I don't know why would you want to build such HTTP client right now, but maybe you need. Then things like having a reasonable timeout by default, not having an infinite timeout as the default. So how many times that we have some outage because somebody in some service forgot to provide a timeout for the REST template. So things like that, failing fast on some silly mistakes, silly configuration mistakes, and basically having an awesome documentation. So this family of libraries solution, is that a perfect solution? Well, let's see the advantages that we got. So first of all, it covers the whole JVM realm. So people writing Scala applications can use Scala frameworks and use our libraries. People writing pretty generic services can use Spring Boot starter and start up quickly. People writing some scripts in Groovy can use the Discovery Service client, for example, and they can communicate with our infrastructure. So things like that, it's very useful. It's quite easy to customize because there are public APIs, there are interfaces that you can implement in order to change some logic. It's quite easy for us to evolve such libraries because, for example, when some user wants to contribute some feature, it's pretty easy for him to know which library he should be looking into and where he should put his changes. And it's easy to drop. So if somebody doesn't like, for example, our solution to metrics, let's say, well, he can just use whatever he wants as long as he uses some conventions that we have in our infrastructure. So, for example, he's reporting metrics to the central storage. But we also have some problems. So, first of all, a problem that we didn't solve using family of libraries is a problem with updates. So, what I mean is that these mechanisms that we implemented in the libraries, they live in the user space, right? They are deployed by the user on some machine. The user uses a library in some version, and when we release a new version of a library, it takes a long time for all our developers to migrate to this new version, right? In open source, you will have users like maybe who will never migrate and will use the old version like till the end of the project. In the company, you can somehow control, who is migrating. You can check who has which version, but still there is a long tail of old versions being used by some older projects. So when you want to introduce a new mechanism, like a new way of registering in your Discovery Service storage, then you will have many months. You will have applications registering the old way. And we don't have, this also doesn't give us solution for non-JVM applications. So for example, let's say somebody is using Golang or Python. We have such applications in our infrastructure where basically these libraries don't give them anything. They give them a reference implementation of what you need to do in order to be compatible with our infrastructure. So they can look up the code and see, okay, I need to send my metrics using this prefix into this location, okay. But they need to do code it by themselves in their applications. And yeah, that's a lot of projects, so it gets quite large. I mean, all these libraries, the Spring Boot starter, it's, you know, it is a reasonable amount of code that you can introduce bugs into. So a third approach that we try to use as much as we can is to provide a rich environment. So what I mean is, let's say we have our application. So each cloud is a different application. And let's say we want to change some mechanism, like a new way of registering in our discovery storage. So then, you know, you need to update. A user decides to update his application. He updates his application, but then, oh, there was something wrong in the mechanism, so we need to roll back. Okay, so he had to roll back. Then we provide an even newer version. He updates, and then all the other applications can update. And one application on the left, you know, didn't update for months because the project was no longer developed. It was just maintained. So that's a problem because this code lives on the client side. We don't have control over who updates when, and we have this long tail of updates. So an approach we can take is to provide sidecar processes. So processes that are running on our machines. So if we have common machine images, or we use containers, then all our services are running on some shared infrastructure, on shared like machines, shared environment. So we can provide to the environment another process. Let's call it, for example, discovery service process. And so along the service, there runs a small process that is responsible for registering and unregistering in discovery service. So when the application starts up, this process notices it. He sees that the application is up, so it registers it in some discovery storage. Then when the application goes down, this process is constantly monitoring. It sees, oops, the application is dead. Okay, so I need to unregister this application from my storage. So, you know, now this discovery logic of registering, unregistering can be removed from the client side, removed from the library. We have a more lightweight library, and the developer of such discovery service mechanism is free to update whatever client he wants. He can update first some single service, some small subset of production machines, and then he can upgrade everything, and the users don't even have to know that something changed. So that's an approach we try to take every time we can. So things like configuration service, so a REST-based service for storing configuration, where it's very easy for services to read configuration. They just need to make some HTTP call. So again, we don't need to keep this mechanism of reading configuration on the client side. We can move it to a centralized service. So the more code we put into the environment, the less code we have on the client, and the easier it is to to update versions and to evolve. So to conclude, 3 approaches that we use over time. All-in-one framework, it was useful in the beginning, family of libraries that we still use, and rich environment, which helps us with updates and with non-JVM applications. And principles that we have in mind when we are building our application, our libraries. So as you can see, these are basically good old object-oriented design principles, but in the domain of building libraries, they are more important maybe because this logic lives in the client side. You cannot simply just refactor things later if you mess up. If you mess up, you have to stick to the API so that you committed to. So it's important to make things right from the beginning. So that's all I have prepared, and now it's time for questions. We have still a minute, I think. Anyone? Okay, if there are no questions, you can contact me in the corridor and or ask me on Twitter. So thanks a lot.